In this lesson, we're going to continue our discussion of beams, and we're going to be focusing especially on combined loads. So looking at this problem, we have a rod that is attached as a cantilever beam to a surface on the back edge, back here. And on the front edge, we're going to say that this rod is attached permanently to some sort of arm. Maybe it's welded on or something like that. And there is 1,000 pounds that's being applied to the edge of this arm. So we're going to call this length of the arm L, and we'll call the length of the rod A, and then the diameter of the rod also comes into play. We'll say it's 1.5 inches. Now before we actually start calculating what these ought to look like, let's just take a minute and think about what we should expect. If I look at this back edge, and let's say for a minute that we disconnect the joint back here, and let's see what would happen. So first off, if we just completely disconnected it entirely, we would see that this whole assembly would fall straight down. So I know that there's some sort of force being applied in the upward direction back here. Okay. Also, we could imagine maybe that this rod is running inside of a bearing. So now it's being supported in this vertical direction, but it's allowed to rotate, and we would expect that this 1,000-pound force would cause this to be rotation. So there's a torque that's trying to torque the rod about its axis. And finally, if you were to consider that this bearing that's in the back is just a pinned joint, we would expect that the rod would try to tip down. So there's also a moment. So there's three different loads that are happening at that back edge. There's a force that's opposing the force of the 1,000 pounds. There is a torque that's opposing the twisting of the cylinder. And there's also a moment that's opposing the bending of the cylinder at that back edge. So let's take a minute and see if we can draw some free body diagrams and calculate what those forces are. So here we have the rod in the loading condition. And the first thing I'm going to do is draw a free body diagram of this front arm. So let's just try to do some sort of approximation of what that free body diagram might look like. Let's put some circles to represent the holes. So there's a small hole in the front and a large hole in the back. Okay, something like this. A force in the downward direction here, and we can say that that force F is equal to 1,000 pounds. F is equal to 1,000 pounds. We would need to recognize that there's going to be some sort of reaction force. Maybe I should call it R1. So I have a reaction force, and just by inspection, because those are the only two forces that are being applied, by summing the forces in the y direction as I have shown, I'd know that R1 is equal to F. They're both equal to 1,000 pounds. And then finally there is a resistance to twisting. So it is inside here, the attachment to the rod that's preventing this from rotating around. So I'm going to draw it this way. There is a resistance to that rotation, and since the distance from here to here is 6 inches, I'm going to call this value T is equal to. Okay, so this is just coming from doing free body diagrams and analysis of this arm. Okay, so now I have what the torque is that's being applied. So it's a moment in this diagram, and it is experienced. The arm experiences a bending moment, but it's going to result in a torque on the rod. So I'm going to go ahead and call it T for now. Now if I continue my analysis, let me draw another box. And I'm purposely not going to draw it directly below, so we understand that what I'm drawing now is the rod. Matter of fact, let me put a couple circles here to represent the different sides of that rod. So this circle here represents this side over here. Maybe I should label them. I'll do that in just a minute. So let's label our locations. Let's call this location at the cantilever spot. Call that location spot 1. And let's call the location on the other end of the rod where it attaches to the beam, to the arm. We'll call that 2. And then we'll call this location here at the end of the arm where the force is actually being applied. We'll call that 3. So using our notation then, what's happening right here, this cross-sectional area here we'll call, this is the cross-section of the rod at 1, and this is the cross-sectional rod at 2. That's what we're interested in seeing, how these ought to affect. So let's draw a free body diagram now of the rod. This becomes a little bit more challenging because we've got things bending in both directions. So first, there's a reaction force R1 in the upward direction on the arm, so there needs to be an equal and opposite force at the end of the beam. There's a reaction force here. I could call it R1, or maybe if I want to, I could call it R2, but I know that it's going to be equal to this same value as the top. So now we're 1,000 pounds in the negative direction. And so opposing that, on the cantilever side of the beam, there needs to be, this is what I'll call R2. There's a reaction force down here. So R2 is equal to 1,000 pounds. 1,000 pounds. And now we have a torque. If there's a torque in this direction on the arm, or around the arm, then that's going to be worked out as a torque in this direction around point 2. And again, that's going to be 6,000 pounds. So that means opposing that torque on the other end, we would have a torque that's going the opposite direction, and it would have the same value. Okay, and then finally, we're going to be creating some sort of moment. So let's draw that with a different color. So this torque is, this force down here would be trying to put a moment this way on it. So it's going to be opposed over here. And so my moment would be equal to 1,000 pounds. So out here the moment is created by R1. By here the moment is created by the reaction of the cantilever with the edge of the rod, and the moment that I would expect here at the beginning would be equal to the 8 inches of the rod times 1,000 pounds, or 8,000 pound inches. And again, we can calculate this by summing forces. 8,000 pound inches. So we could do a free body diagram and summing forces in the x and summing torques around a point. Let's say x is equal to 0. So one last step before we can move to making our diagrams. Let's go ahead and say that we'll call this direction here our x direction. So that's where x is equal to 0. So there's our x-axis right here, where x is equal to 0. Okay, so I have all the pieces now. So let's go back through, and if you're not convinced by what I'm doing, a little bit of a, I'm not really doing all the details here. I want you to go back and look at this on your own and see if you can figure out how I got the 8,000 and the 6,000 and the direction of the arrows and all of the details. But let's move forward now to some diagrams. So here is the loading diagram. And again, the x is equal to 0. This is where the cantilever is occurring. This is going to be x is equal to 8 inches. This is the end of the arm, the end of the rod where it's attaching to the arm. So for our loading diagram, we have 1,000 pounds up and 1,000 pounds down. They're point loads at the ends of the beam, or of the rod. For our shear diagram, it's just a step of a positive 1,000 pounds. So all along the rod, the shear is equal everywhere. For a moment diagram, there's no moment there's no force or no loading condition creating a moment where the arm is actually attached. It's being caused because the force is cantilevered a distance away from the edge. So there's a moment right at where x is equal to 0, right at the cantilever location, and then it goes to 0. And then finally we need to consider torque. So torque is the attempt of the arm to twist the rod, and we've found that that was equal to 8,000 pounds, and we'll say it's positive and it's constant over the whole beam. So looking at the rod now, it's obvious that the worst loading condition occurs right here where x is equal to 0. That's where you have the highest combination of shear, moment, and torque. And in this particular problem, that's the only cross-section we'd have to equal. We have to examine. So it's very important that we understand that the only reason we're not having to examine other places along here is because it's obvious that this is the worst location. So for instance, if shear maybe dipped down lower and came up higher, or if these were all functions of x instead of be constants of x, I'd need to look at multiple spots along here possibly. Look at multiple cross sections. But in this condition, in this loading condition, the only one I have to consider is where x is equal to 0. So let's take a look at that cross section. So here's that cross section where x is equal to 0. And the first thing I want to ask myself is, where does the worst stress occur because of the bending moment? So if you recall this diagram, we know that the bending moment happens the furthest distance away from the neutral axis. So right there at the top and right there at the bottom in compression, that's where the worst spots happen. So there's the two locations that have the worst stress due to the bending moment. Okay, so let's hang on to that knowledge. Now let's look at where does the worst stress occur from the shear force. And here's the diagram that goes with that. And the worst case, the worst location is any place where y is equal to 0. It's the entire line across that. Okay, so that's another location that we might need to consider. And finally, we need to consider where's the worst stress from torsion, and the torque is causing a stress along the rim of the part. So we also need to recognize that the worst case of stress caused by torque is along the rim. So taking a look at these three contributions of stress, if shear is worse here because of the transverse shear, and shear is worse here because of the torque, it's really only this point that we need to measure. And this point and this other edge. One of the edges, the shear it's shown in the up direction as diagrammed here. Diagrammed here, the shear is pointing up, and the transverse shear here was also a positive value. So this point right here on this edge is going to have positive shear because of the transverse loading and positive shear because of the torque, so the two of them would sum. On this end, you would have positive shear because of the transverse shear and negative shear because of the torque, and so they would somewhat cancel each other out. So this right here is an important location. The other location is happening up here where you have a maximum moment and a maximum shear from the torque at the same location. So we're going to consider these 2 points, points A and points B, and it's important that we understand why we're not having to consider anywhere else on the diagram but those 2 points. Okay, so let's take a look at point A now. So there's point A up here at the top. We can calculate the stress caused by the moment. Okay, so here's our C. C is d over 2, the diameter up there. We can calculate what I is, and we get basically 18 kpsi of stress up there at the top. Our formula for shear stress caused by the torque is Tr over J. So again, we can calculate what that is. This is going to give us that the torque caused by stress is about 12.1 kpsi. So plugging this into an applied matrix where we have torque and normal stress. And notice the normal stresses in the other two directions are equal to 0, and all of the other shear stresses are also equal to 0. If I take the eigenvalue of this, so it's looking for the principal stresses, we can get that the principal stresses are 24, 0, and -6 kpsi. And then using a formula for the maximum shear stress, that's going to give us the maximum shear stress is 15.1 kpsi. Okay, so these are the numbers we need to look at to consider which place is worse. So now let's consider point B. At point B, there's 0 stress caused by the moment. We do have shear caused by transverse, and we have a formula for circular cross sections that says that 4v over 3a, and that's equal to less than 1 kpsi. We also have the torque, the shear stress caused by the torque, and again this is the same as before. It's going to be equal to that 12.1 kpsi. And now again, this is the location where the two of these are summing up, so you get 12.8 kpsi. Okay. So taking this value now and putting it into a matrix. So in this loading condition, there is no normal stress. It's all shear stress, and so all of the diagonals are 0. And we could again do eig of this, and we're going to get what we would expect, that the maximum is 12.8 and the minimum is -12.8, and the maximum shear is 12.8. So all of these have the same value, which is what happens if you have a case where everything's in pure shear. So what does that mean for us? That means that when we look at this particular beam with this particular loading condition, at the end of the day, we can recognize that if you put 1,000 pounds on this arm, the maximum stresses are going to occur up here at point A. We have the highest in tension, and we have the highest maximum shear. And what we need to start considering now is how do we take these numbers and look to see whether this part would fail. So these are the 2 points that we could consider. So even though A has the higher max stress, both points needed to be checked to be able to confirm that point B has a lower maximum stress value than point A. And I should point out, if there happens to be a material out there that fails because of compression much easier than it does because of tension, point B might be the place where failure begins to occur. So if the material is even, in other words, if it has the same strength in compression as it does tension, then point A definitely has the worst condition. And if the material is going to fail because of shear, then again point A is the worst condition, since it has 15 kpsi compared to point B, which only has 13 kpsi.